We are diving straight into the deep end of AI today, focusing on, really, the fundamental challenge of building a system that doesn't just generate video, but genuinely understands the real world. And since you're already familiar with machine learning and data science, we're skipping the basics. We're going right to the core conflict, the battle to create a true world model.
Exactly. And that conflict really pits OpenAI's Sora, the current champion of diffusion transformers and a heralded world simulator, against Meta's V-JEPA. V-JEPA uses a joint embedding approach to try and force the model to capture a deeper, more structural understanding of reality rather than just statistical patterns.
And what makes this source material so compelling is that it just dismisses the whole scaling cures all argument. The authors argue that both Sora and V-JEPA are, well, fundamentally flawed. They lack the necessary cognitive architecture to move beyond simple pattern recognition.
Right. And to prove it, they pull out a pretty unexpected weapon, a modified Kantian philosophical framework, the theory of productive imagination.
Okay, I have to stop you there. Kant, are we really saying we need 18th century metaphysics to fix diffusion models? Isn't that a little esoteric for deep learning?
It sounds it, I know, but the paper frames it perfectly as a practical engineering problem. I mean, Kant was trying to figure out how humans synthesize fragmented, chaotic sensory input, which is exactly what a raw video stream is, into a singular ordered reality. The paper isolates three indispensable components that the AI must internally possess to synthesize that input into what they call a coherent world model, or CWM.
A CWM. So think of it as the AI's foundational internal rulebook.
Precisely. And it's something you can't just get by feeding it more data. It has to be built in.
Okay, let's unpack that rulebook then. What are those three mandatory components?
So first, you need representations of isolated objects. That's the easy one. The system has to know what an object is. Second, and this is critical, it needs an a priori law of change across space and time. This is the model's internal universal physics engine, basically, ensuring movements and interactions are plausible. And third, you have to systematically implement what they call Kantian categories of pure understanding: quantity, quality, relation, and modality. Think of these as the constraint filters that the physics engine has to use.
So this deep dive is essentially an architectural audit. We're mapping the flaws of Sora and V-JEPA against these three requirements and then looking at the paper's proposed solution.
Exactly. The Coherent World Model Learning Architecture, or CWMLA. We start by seeing how the CWM is supposed to be built. The core challenge is taking all that disorganized data, all those clips, and synthesizing it into a single coherent experience.
And the categories provide the structure that makes that synthesis possible. Okay, let's translate this for our audience. Let's take quantity. What's the real-world consequence if a system is missing that constraint?
The consequence is representational instability. Without that innate schema for quantity, the system just can't reliably determine the count of things in a scene. You ask it for 2 dogs, it might start with 2, end with 3, or have one dog kind of visually merge into another. It's the kind of instability we see where objects just appear or disappear for no reason.
That makes perfect sense. It's not just a generation glitch, it's a failure to define the totality of the scene. What about relation then, specifically causality?
Causality is just fundamental for understanding time. The schema for cause and effect establishes a rule-based sequence. It says certain conditions reliably lead to certain outcomes. If the AI doesn't have this, it generates sequence A, then B, but it fails to encode the necessity of it. It doesn't know that striking a match must come before the flame, or that the flame will only go out if you blow on it.
So the categories are recognized through these internal schemata, which are basically hard-coded rules for sequencing time and data.
Yes, and that brings us to the a priori law of change.
Right, so the authors have essentially derived a universal physics rule set from this philosophical work. How does that law practically govern a generated video clip?
It acts as the plausibility filter. It governs how objects can move, deform, and change. But here's the nuance. The law of change is context-dependent, and that context is provided by the categories, especially quality.
Give us an example.
Sure. The law of change applies differently to a rigid object, say a steel ball, versus a pliable one like a rubber hose. The AI must first understand the object's physical property, its quality, to apply the correct constraint. The law prohibits the steel ball from suddenly flattening. It allows the rubber hose to bend. So the system has to recognize quality before it can execute the law, you see.
I do. And the authors also point out that experience is required, which goes beyond the original Kantian scope.
Yes, that's a key extension. The CWM needs 2 inputs: the fragmented perceptual data and also structured experience. This gives rise to three essential operational modes. First, you have reality tracking mode, which relies mostly on incoming perceptual input.
When a scene is new.
Exactly. Then there's dreaming mode, where it relies solely on internal compositional thoughts or stored experience. This is what happens when you generate from a text prompt. And finally, mixing mode, which synthesizes both perception and past experience to, enhance its understanding.
And to keep the AI from just drifting off into fantasy, the analysis requires a reality check module. This sounds a lot like predictive processing concepts.
It is, absolutely. The CWM uses this module to predict future scenes based on its internal rules, and then it compares those predictions against the actual incoming perceptual data. Any mismatch forces the CWM to adjust its biases and refine its own rules. It establishes a continuous learning loop.
Okay, we've established the theoretical rulebook. Now let's see what happens when the biggest world models, Sora and V-JEPA, are measured against it. Starting with Sora.
Right, Sora. Fundamentally, a diffusion transformer trained on, massive amounts of video data with descriptive captions. The diagnosis is that Sora's architecture, by its very design, fails to systematically enforce these CWM constraints, the law of change or the categories. The video compression and the nature of diffusion mean Sora operates predominantly in the dreaming mode.
So it's an incredible experience composer, but it's not anchored to any foundational physics engine.
Exactly. It's anchored to statistical distributions, not a rule book. And the evidence is right there in the videos.
What stands out as the biggest failure of the a priori law of change?
The causality errors are, well, they're damning. Look at the famous glass video. The size of the glass randomly changes. That's a failure to constrain shape, which is linked to the category of quality. But worse, the liquid spills out before the glass lands. That's a fundamental violation of temporal order and causality. The model knows statistically that liquid should spill, but it doesn't know the necessity of the sequence.
You also see failures related to just basic physics, like anchoring and rigidity.
Yeah. Yes. A heavy object like a treadmill inexplicably drifts side to side. That violates the law that should anchor heavy objects. A plastic chair randomly changes shape, showing it doesn't understand its own inflexible nature. Again, the category of quality is just missing.
And what about quantity, that instability we talked about earlier?
We see it clearly in the wolves video. The scene starts with 3 animals, but then it randomly shifts to 4 or more without any of them actually entering the frame.
Right.
The model lacks the constraint that says one object can't just become 2.
And the basketball example?
Even more basic. The basketball passes through the solid rim. That's a failure of the law, prohibiting solid objects from passing through each other.
And the birthday candle is maybe the simplest causality test of all.
It is. The woman blows on the candles, and the flame remains completely unaffected. The expected outcome just doesn't occur. It's actually quite humbling, isn't it?
It really is.
And crucially, the authors emphasize these are not just technical glitches you can fix by scaling up. They are flaws stemming from the fundamental absence of these constraining variables in the CWM structure.
So if Sora's problem is being completely unconstrained, VGG is kind of the architectural antithesis. It's designed to be grounded in prediction, right?
That's the idea. V-JEPA tries to learn representations by predicting missing patches in masked video clips, but it does so in a latent space using these context and target encoders. It's all about minimizing prediction error.
And the paper does acknowledge it has some success. By predicting those missing chunks, it manages to grasp the context-dependent parts of the a priori law of change, at least over short time frames.
It does. It knows, for instance, that a hand won't just spontaneously transform into a shoe in the next few frames. That is its strength. However, V-JEPA still fails to realize the complete coherent world model. The biggest limitation is the training data duration. It's just 2 seconds, 64 frames.
And that's just not long enough.
Not at all. It inherently limits its ability to capture the longer-term causal chains that are necessary for a truly robust law of change. If a cause and effect take longer than 2 seconds, V-JEPA is going to struggle.
And we run into the categories issue again, even with this more grounded approach.
Precisely. The training, of focusing on patch reconstruction doesn't explicitly integrate all the Kantian categories. And this shows up starkly in its performance on multi-actor tasks. V-JEPA's accuracy on the complex AVA dataset, which requires distinguishing multiple people and their interactions, is only 25%.
That low AVA score is really telling, isn't it? It implies it has trouble keeping track of who is who, that's quantity, and what one actor is doing to another, that's relation and causality.
Exactly. It captures correlation beautifully, but without those hard-coded category constraints, its CWM is incomplete. And finally, V-JEPA is non-generative. It can't simulate or incorporate genuine experience. It only implements a tiny fraction of the productive imagination.
So we have Sora, great at composing experience but lacking physics and constraints, and V-JEPA, which is grounded in short-term reality but lacks the full cognitive architecture and experience. This brings us to the final contribution, the CWMLA.
The coherent world model learning architecture. It starts with a clever adaptation of V-JEPA's approach to force structure into the encoder. In the initial phase, a target encoder processes fragmented or out-of-sequence clips, and its output is forced to match the output of a frozen video encoder that's processing the original orderly clips of the same scene.
That alignment loss function is brilliant. It forces the target encoder to internally learn how to synthesize the disordered data into a properly structured CWM representation. But how do you systematically inject those crucial Kantian categories into this?
Through the AI cognition module. This module is explicitly trained using detailed video descriptions that incorporate all the Kantian categories through text. This is vital. For example, the text prompt must explicitly detail an object's flexibility, whether it's rigid plastic or pliable fabric, so the encoder learns its quality, which then leads to the correct application of the law of change.
And once that core CWM structure is learned, the CWMLA moves to its last phase, which builds the continuous, iterative engine that mirrors human cognition.
This is where it all comes together. The frozen target encoder provides the CWM parameters, the synthesized reality. This data is then fed to the frozen AI cognition unit, which generates text descriptions. And crucially, this unit integrates with large language models to access related verbal experience. That's the abstract knowledge that visual models alone just miss.
So if the visual cues are ambiguous, the LLM provides the abstract causal knowledge. It's filling in the experience gap.
Exactly. This combined data then fuels a frozen diffusion transformer, our experience engine, to sample coherent dreams. But the key element is the productive imagination mixer. It synthesizes the CWM parameters from reality and the generated experience from the dreamer. And this mixer is trained via the reality check loss function, comparing its predicted future scenes against actual incoming perceptual data.
So the system is constantly forced to check its internal narrative, its dream, against what reality actually delivers.
Precisely. The outcome is a holistic framework where all units are continuously updated. The system can function in all three modes, reality tracking, dreaming, and mixing, using both objective and subjective knowledge flows. It finally gets an anchored, temporally accurate understanding of the world.
This has been a fascinating journey. We used Kantian philosophy to reverse engineer the requirements for a coherent world model, and then diagnose the architectural flaws in Sora, which is stuck in dreaming mode, and V-JEPA, which is grounded but incomplete.
And the core takeaway is just so clear. The path to AGI through world simulators is not about collecting more data or scaling parameters. You cannot simply diffuse your way into understanding reality. It requires implementing these foundational cognitive structures, the categories, and the a priori law of change to ensure the model is detailed, accurate, and anchored.
The component parts for this architecture, advanced encoders, Sora-like diffusion models, LLMs, they all already exist. But the real innovation is unifying perception, imagination, and understanding into this continuous, iterative cycle.
Indeed. Now, here's something for you to consider. If this final CWMLA architecture, using LLMs to access vast verbal knowledge, successfully creates a truly coherent world model, how might such a system move beyond mere video generation? If it truly possesses an internalized constrained physics model, how quickly could it adapt to exponentially complex novel reasoning, planning, and simulation tasks that truly demonstrate general intelligence? That structural grounding is the critical bottleneck we are now trying to break.